So good morning students. In last class we discussed about Werner's theory. So Werner, the primary and secondary valency, ionizable, non-ionizable, he told. So after that, what are the failures of Werner's? See, failures of Werner. See, what he perfectly explained means, so ionization. So ionization is explained. How many possible complexes also explained. So ionization, which is soluble, which is not soluble. So how many possible complexes. Next also explain about conductivity also. See, number of ions are possible means according to that conductivity is also explained. But where is the failures? So he does not explain about stability. So stability of a complex. Next, shape and structures. So stability also not explained, shape also not explained. Next, they are showing color properties. Complexes are showing color properties, that also not explained. Next, magnetic properties. So magnetic properties also not explained. For the explanation of this, some other theories are kept. In that second one, so that is VBT, Valency Bond theory. So second theory, we are going to discuss about VBT. So Valency Bond theory. See, actually in your chemical bonding means normal compounds. In normal compounds also Valency Bond theory we are discussing. In that what? So mainly it is explaining the sigma bonds and pi bonds. So here, so one by one we discuss the points. So complex contains metal. So that is a central metal and it is surrounded. It is surrounded with ligands. He told. Next, every ligand is donated a pair of electron to central metal ion. So metal has empty orbital if it has a pair of electron also. Next, ligand contains lone pair, and if some ligands have empty orbitals, if they are not possible also, mainly compulsory lone pair. This lone pair is donated to central metal ion. This is called as a sigma bond. So which type of bond? For one bond formation requires two electrons, that two electrons are supplied by one only. So that's why this bond you called as a coordination covalent bond. Covalent bond. So based on this, so previous we called as a complex compounds. So now the word complex compounds is converted into coordination compounds. So because of formation of coordinate covalent bond, from ligand to metal is a sigma bond. If ligand contains empty orbitals, then metal also supplies its lone pair to this. This is called as a pi bond. So metal to ligand is pi bond, ligand to metal is the sigma bond. Next, who is responsible for structure and hybridization, everything? The sigma bond is the responsible. So that's why this theory explains the shape of the metals, means complexes. So now we are discussing. First point is formation of coordinate covalent bond. Next, second point. The sigma bond. The sigma bond is responsible for structure and hybridization of a molecule. So based on this concept, so he explained structures and hybridization of the complex compounds. Suppose if Ml2 complex is there, so that means what? Two ligands are surrounded to the metal. So in what way? Metal is the central, two ligands are donated. So how they can donate? In the linear manner. So two sigma bonds. So the hybridization we called sp. The structure is linear. The bond angle is 180. If Ml2 is there. Next, if Ml3 is there, so that means metal is surrounded with three ligands. So that means the structure, the hybridization is going to 3 number. So one is sp2. So 1 plus 2, 3 number. So that is the structure is trigonal planar. So also you write a TGP. So the bond angle is 120 degrees. Next, see Ml4. Ml4 means metal is surrounded with 4 ligands. So how the possibility is there means, so we have two possibilities. So 4 ligands are arranged in tetrahedral structure. So the hybridization is sp3. That structure is tetrahedral. Also they can write as a TD. So bond angle is nearer to 109 degrees, 28 minutes. Next, another possibility. So 4 ligands in square form we can write. So central metal is surrounded with 4 ligands. So in square planar structure, if you see the hybridization, that is DSP2. So square planar. Next, bond angle is 90. So if d orbital is involved, so based on this also he classified into inner orbital, outer orbital complexes. In next point we are going to discuss about that one. Next, in this Ml4, next Ml5. D. So Ml5. So central metal is surrounded with 5 ligands. So here also we have 2. So metal is surrounded with 5 ligands. So like this. So in what way it is 3 corners, trigonal is like this, above 1 and below 1. So this is a trigonal bipyramid. So trigonal bipyramid, this is also represented as a TBP. Suppose you see the bond angles here to here, it is 90 degrees. Next, in this 120 degrees, straight line 180 degrees. So this is one possibility of 5. Next, another possibility. So hybridization you can write sp3d. So D is outside of that. Next, why it is writing after the SP and before the SP, we will discuss that also. Next, another possible structure, central metal is surrounded with 5 ligands like this. So another possible structure. So the hybridization is DSP3. So 1 plus 1, 2 plus 3, total is 5. This is the square pyramid. So square pyramid bond angle is 90 degrees. So 4 are like this. Middle is metal, 4 ligands are like this above 1. So that is the square pyramidal structure. But you observe, sp3 after D is there, sp3 before D is there. So based on this possibilities, one more classification he classified about the complexes. We will see next class. Next one. Next, E. You take ML6. So means 6 ligands are surrounded to the metal. So how we can write? So 6 ligands are donated to the central metal. So it is looking like this. So it is a square. Metal is the central, 4 ligands are there, above 1, below 1. So you can write as a square, above 1 pyramid, below 1 pyramid. So square by pyramid, but famous name is octahedral. It is represented with OH. So what will be the hybridization means sp3d2. So 1 plus 3 plus 2, total 6 ligands. Otherwise, D2sp3. So you must concentrate. After sp, D also coming. Before sp also D coming. Why these two are coming? So that is explained in next point. Next. So last one, ML7. So one metal is surrounded with 7 ligands. How you can going to write? Metal is surrounded. The structure will be. So 5 are in one plane. Next 2 are above 1 is, below 1 is. So like this. So 5 are like this. Middle metal is there. 5 is surrounded above 1, below 1. So that is called as a pentagonal. See, gonal means corner. 5 corners are there. Pentagonal. Above 1 pyramid, below 1 pyramid. So that is a bipyramid. So represented with PBP. So what will be the bond angles? So 360 degrees divided by 5 members. So you are getting 72 degrees. Here to here it is 90 degrees and straight line 180 degrees. So what will be the hybridization? So 7 number is there. 7 number you can write as a sp3d3. So 1 plus 3 plus 3 total 7. Otherwise d3sp3 also. Next here also you must concentrate. So sometimes we are writing after the SPD. Sometimes we are writing before the SP as a D. So that is only going to discuss about the next point. Next. Third point. The complexes are classified. So according to this, he classified complexes into 2 types. So in what way? Inner orbital complex. inner orbital complexes. Simply you can write IOC. Next, another one is outer orbital complexes. So that is OOC. So based on which condition? Based on the d orbital. So based on d orbital participation. So in VBT, according to d orbital participation in the hybridization, the complexes are classified into two types. One is inner orbital complex and outer orbital complex. If you see general electronic configuration of d block elements. So here, what is that? N-1d 0 to 1 to 10. Next, NS 1 to 2. Next, here what? NP also 0, ND also 0. Suppose in the hybridization, suppose inside D is participated in a hybridization. So that means you called as a inner orbital complex. In the hybridization, N-1 d orbital is participated in hybridization, you called as inner orbital. Suppose if outside d orbital is participated in hybridization, then it is called as outer orbital complex. So we will see here, D means what? Suppose 4D series you are taken. So 3D, you take the 3D series elements. So 3D series elements means what? Scandium, titanium, vanadium, chromium, manganese. So that one. In that what happens? This is 3D. Next 4S. Next 4P. Next 4. So 3D. How many? 5. So S is 1 box. P is 3. Here also 2. So suppose a 3D orbital is participated, then you called as inner orbital complex. So how the possibilities are there? So one is what? D, sp2. So previous we discussed. Next D, sp3, D2, sp3, D3, sp3. So these combination, before you are writing D means that is a 3D orbital, otherwise N-1 d orbital. These are called as inner orbital complex. Next, if 4D, otherwise ND is participated. So what are that? You can write sp3D. So sp3D2, sp3D3. Suppose these are participated means you call it as outer orbital complex. Next. So one point is inner orbital, another one is outer orbital based upon the d orbital participation in hybridization. Next, another also based on the spin of the electrons. If you see that one. So fourth point. So he explained about some concept about ligands. So ligands also. So ligands also he told that some ligands are strong field ligands. And some ligands are weak field ligands. and he given something because of a strong field ligand. Some examples of what he given: cyanide is a strong field, he told. Carbon monoxide also strong field. So weak field ligand means halides we are taken. So what are that? Cl minus, Br minus, I minus, F minus. These are weak field ligand. So why strong field? Why these are weak field? It doesn't explain. That become as one of the failure. But you must understood the point. Ligands are also classified into two types. One is a strong field, another one is a weak field. Next, what happens in the presence of strong field ligands? In the presence of strong field ligands in metal, the unpaired electrons are paired. The electrons are pairing. So electrons are pairing means what? Spin is decreases. So that's why such complexes are called as, so low spin complexes. So that is LSC we are showing. Next, in the presence of weak field ligand. So in the presence of weak field ligand like halides, then in the metal, the electrons are not paired. So this is very, very important. So in the metal, the electrons are not paired. So then what happens? So as it is, spin is available. So such complexes are called as, so high spin complexes. HSC. Say, suppose starting how much spin is there, same spin is available last. After coming ligands also same spin is there, means you call it as a high spin. Suppose if electrons are pairing in the presence of strong field, such complexes you call it as low spin complexes. So it is another classification according to ligands. So previous we discussed inner orbital complexes, outer orbital complexes according to hybridization. Now low spin complexes, high spin complexes according to ligands. That to be, you must remember. So these are the strong field ligands, these are the weak field ligands. Next. Fifth, magnetic properties. So, magnetic property. In this, what happens? Already we discussed low spin or high spin. Here, suppose the given complex contains unpaired single electrons. Unpaired single electrons, then they show paramagnetic nature. Then they are showing paramagnetic nature. So what happens in paramagnetic nature means in the external magnetic field, the weight of the complexes increases. increases because of the magnetic flux is entering into the complex and this is going outside. So in the external magnetic field weight is increases means this is experimentally it is a paramagnetic. Next, who is responsible? That is unpaired single electrons are the responsible for the showing paramagnetic nature. Suppose if the given complex contains all paired electrons, means that is showing the diamagnetic property. So that is a diamagnetic. Who is a diamagnetic means in the external magnetic field. So weight is decreases. So in external magnetic field, weight is increases. So such we called as diamagnetic substance. Next, he explained that property of unpaired single electrons are there means it is showing paramagnetic nature. If all electrons are paired means that is diamagnetic substance also explained. Next, how to identify paramagnetic? In next we will going to see that one.